guys. Today I would like to review, actually teach you. We haven't really done this part yet, but you guys know about reflection. So I put together the results of your quiz. That was real hard. I just clicked a button saying import grades. On Google Classroom, you can find out how many points you scored out of 15. Again, make sure that when you are using the videos, writing down notes, that you're taking your time. There's no need to rush through this. I'm not giving you an hour lesson every day. I'm trying to shorten that and give you some time to process that information. Miss Tesla just showed up to say hello. Just make sure she doesn't walk across our screen. So today we're going to continue our talk on waves, but thinking about properties and variables that we can measure about waves. One of those is reflection. Reflection is bouncing off a surface. That is one way waves can reflect. Here's an activity that we would have done had we been in class. And if you have an opportunity to do this over the next couple of days, please take this opportunity. It's so cool. You need 2 paper towel tubes. And I'm sure that you can either find paper towels a little bit better than toilet paper because they're longer. You could tape together a couple of toilet paper tubes. I'm sure with the stockpiling of toilet paper tubes that people have those around. If you didn't save any tubes, just now write yourself a note to save a couple of tubes. And here's what you're going to do. You are going to try to get a partner. Someone in your family would be fantastic. And you're going to position one end of the cardboard tube about 20 centimeters away from a smooth surface. So it's like your wall in your living room, your wall in your hallway. And then you're angled it about 45 degrees to the surface shown below. The listener has their tube also angled same distance away and then directed at their ear. So you're speaking, someone's listening, vice versa, switch jobs. You are speaking softly, kind of like we did with our cup experiment. So you're saying something in there like, "You're a great person. I'm so glad that I'm home, socially isolating with you," or whatever. Then what you're going to do is you're going to take your 2 tubes and you're going to leave that flat surface. And you're going to go to a different surface. You could go to maybe, if you were at a wall, you could go to the bathtub. You could go to the kitchen wall. You could go to, if it's different, I don't know if it's different, like if you had wallpaper. I hang the towels over my door, so do it on the towel as your surface. Do it on your bedspread as your surface. So you're going to experiment. If you have a piece of plastic, if you have the car, go to your garage and do it on the car. You're going to experiment with reflecting sound off of different surfaces. And again, it's real hard for me to check to see if you're doing it. I don't live with you, and I can't. If you were going to submit 80 assignments, that would be really difficult for me to go through and give you feedback at this point. So this is honor system. Your brain will really like this. It'll really like experimenting, and it will help you understand where we're going next, which is wave reflection. And I emphasized reflection because reflection bouncing off a surface is going to be different than what we talk about in the future. The activity that we would have done with our light stations, which are also pretty cool, is reflecting light. So we would have looked at not only reflecting sound, but reflecting light waves. And so that sound, that mechanical wave, would possibly act differently than an electromagnetic wave. So we'd have these light boxes, and we have set up a flat mirror. And in physics, something that's flat, like this flat mirror, is called a plane mirror. And it's plane as in this kind of plane, I think. Now that I'm saying it, I'm like, am I right? Yeah, plane mirror. So a plane mirror just means completely flat. trying to draw a flat line. That's not real easy. So that is not a plane mirror. That is a bumpy, wiggly mirror. The mirror that I would have given you is plain, and you can see the little hooks, and then there's a little angle diagram on there for you to make some predictions. So we are going to look at this plane mirror. You get your lab aids cards, and you've got these different lines measured. Right here is the mirror. So this whole circle is because of the reflection. So you know that some surfaces are reflective and some surfaces are absorptive. Reflective surfaces, we talk about reflecting light. They can reflect sound. There's other waves that can be reflected when you're thinking about the radio waves and how I'm sending out radio signals with my giant radio telescopes, and things get reflected to come back to us, and then other things are sending out radio waves as well. So in this image, we are wondering if we shine a light with a laser, a pinpoint light. If you have some sort of laser, the flashlight light is a little bit too wide. If you have a narrow laser light, this is fun to experiment with as well. If I shined my flat, really thin, pointed laser at my flat mirror, my plane mirror, and it's coming in at this angle. So this angle, if I had looked at the previous diagram, it's labeled 1L, 2L, 3L, 4L. These correspond to left. So the first left, second left, third left, fourth left. The fifth is straight down the middle, and then you've got the numbers on the right, 1, 2, 3, 4. If this is a plane mirror and I am going to shine my laser pinpoint onto one left side, where is it going to come out on the at all, right? Where is it going to come out? Is it going to direct right back? Is it going to bend a certain way? How is it going to reflect? So go ahead and give that a few minutes of thought and make a prediction. If you'd like to write a prediction down in your science notebook, great. Give you an opportunity to make a prediction. Here's the reflection. When I shine in the light at a 1L, 1 on the left, this is considered the angle of incidence. So you're seeing here, we have a little bit of geometry going on. We have our flat plane. I guess you can't see me pointing at the screen. That's weird. You have our surface, our planar surface, that flat mirror. When I shine in this light at this angle, the reflection is equal and opposite. 1L reflects to 1R. This angle of incidence, and I could measure the angle of incidence from the plane mirror surface to the light, is equal to the angle of reflection. There's an angle of incidence and an angle of reflection. In geometry and science, you know how much we love writing words. So the symbol for angle is oftentimes like that. And it doesn't have to be like that angle doesn't have to be perfect. The angle of incidence would be the angle of I. The angle of incidence is equal to the angle of reflection when the mirror or the surface is planar, flat. When is the angle of incidence equal to the angle of reflection? When the surface that the light or wave is bouncing off of is planar or flat. This image, of course, I've just been perusing Google Images, and I really liked this image because it shows us that there's an incident wave, and it looks like the IN got cut off from me screenshotting. The incident wave and the reflected wave are showing that this angle of incidence here is equal to my angle of reflection. And if those two variables are the same, what you know to be true is the reflecting surface is planar. The reflecting surface is flat. And in science, in physics, flat would be planar. And I think, you know how good I am at spelling, plane R, A-R, I'm pretty sure. A flat planar surface gives us equal angles of incidence and angles of reflection. Light, this could represent a radio wave here coming through. So the lines that you see often, like the ripples of a pond, if it gets disrupted, show us usually the crests of the wave, because we're seeing it from a cutoff perspective here. The reflecting surface matters. And you can see, like, so far I've been really emphasizing if the surface is flat or planar, these things are going to happen. Well, if the surfaces are not flat or planar and they're bumpy at all, you'll get some reflection that is different than the angle of incidence. So this angle coming in to this surface won't be equal in the angle of reflection because this surface is not flat. So this is why light gets spread out. If I had an angle of incidence, if I go back to this image and I want to pinpoint a light, I need to have a flat surface of reflection. You'll notice that sometimes the reflective surfaces spreads the light out. Sometimes when that light spreads out off of different surfaces, I might see different colors depending on how the wavelengths are broken up. So I can manipulate my reflections of my waves based on surface. So that's pretty cool thinking about technology and what I would do. This is an example of a diagram that shows if I had this shape in my band room, for example, this could represent a sound wave, this could represent light waves. If this were a light wave and I had, and I wanted to pinpoint light on a stage, if you think about stagecraft, as this angle comes in, it reflects. As this angle comes in, it reflects. And you'll notice the angle of incidence coming in and the angle of reflection are different. And you'll also notice that this surface is called concave. No, that's incorrect. This surface is called convex. This surface is called convex, and you know it's convex because it bulges out. That bulging out. So I'm shining my light on the bulging out surface. And that bulging out surface is creating angles of reflection that are different than the angles of incidence. And if I have all this light coming in, when it hits this convex bulged out surface, the light's going to spread out. And when it spreads out, it might go and dissipate a little bit. Think of this as sound. If the sound comes in, because waves could be sound, waves could be light. If the sound is coming in and it's bouncing and it's really bouncing and it's not a concentrated bounce, the noise I hear it's going to be muffled or spread out and it's not going to be understandable. So if I wanted to take the same area-ish and concentrate the energy, those waves are transmitting energy, the energy of the light, the energy of the sound, I could do multiple convex surfaces. And those multiple smaller convex surfaces are going to have similar angles of incidence and angles of reflection, but it's going to squish them into a closer area. So if I get this kind of bouncing around of wave reflection, I can really pinpoint and isolate my light and my sound to make it exactly what I want it to be. This right here, in thinking about sound and how sound reflects, is a huge part of architecture and designing concert halls, designing churches. One of the things about the Notre Dame that's really challenging and difficult is one of the historical awesomeness, amazing factors of the Notre Dame was its sound quality. That when you went in there, the way that the sound reflected was amazing. And so when the fire happened, one of the concerns was, oh my gosh, how are we going to get it back to that technology? And think about when that was built. And think about how waves have been being used in technology for a very long time. The other thing I wanted to show you is when things curve. So we get curved mirrors, and we make mirrors curved for a reason. And if you think about objects that use and need mirrors, what comes to your mind? I don't know what comes to your mind. The first thing that comes to my mind is a telescope. So telescopes and there was mirrors and microscopes as well when we were using a different technology that wasn't as, when we didn't have electricity. We needed to bounce light off of things. So if I have this is my convex surface, that convex curved out. Oops, I took away my little pointer here. This light reflects and spread out. The light reflects and spreads out. This light comes in. So the diverge, spread out, divergent, go apart, divide, diverge, divide. If I want to divide my sound, if I want to divide my light, I want to spread it out, I need a convex surface. If I want to converge and bring my sound and my light together, I'm going to use a concave surface. And I always, you saw me earlier when I was like, oh, what shape is this? And the vocabulary, sometimes I have to review, right? I have to remember, oh, yeah. Concave is bent in like a cave. That's how I remember that. And so convex has to be the other thing. The concave, that mirror, that inside of that mirror that's bent like that, that's curved, when the light or sound comes in, it comes in and reflects. Angle of incidence different from angle of reflection. And all over this surface, the angles of reflection will converge at a focal point, at an F point. So if I want to concentrate my sound and light, I would use a concave surface. If I want to spread out or diverge my sound or light, I would use a convex surface. And then here is a way that I use that technology. We use mirrors and different shapes and surfaces for reflection to bounce around light so that we can see things that are really far away. Or we can view things that are difficult for our human eye to view. So we've got all of this technology, and I would love to know more about mirrors in technology. So, if you have a couple extra minutes and you want to look that up, that'd be awesome. Send me a message, let me know. I would appreciate that. I'm just scratching the surface here. Another technology use of reflection with sound is the bat sonar. The sonar is sound. The bat is actually emitting a sound. And that sound wave, this big yellow sound wave, leaves the bat, travels through air, the medium, hits an object, and bounces back. It's spectacular, the biological evolution of bats and other organisms that use echolocation sonar to be able to not only detect prey, but possibly predators, and then obstacles. Think bats flying through a forest, bats looking for not only prey, but things to stay away from. This is cool. And so the bats will use, and we saw that remember that sound PBS special that I showed you in class not too long ago? We saw that bats actually detect such specific information about the insects They literally can see parts of the insects and how to really hone in on catching that insect. Awesome. One of the questions is, because we understand about reflection and we're starting to learn about sound reflection and light reflection, why do you suppose many mammals have curved earlobes? Or what do you call that part of your ear? Not the lobe is this. Curved ears. If you go ahead and look up ears on mammals, you're going to get some real cute pictures. This little mousy mouse, he's real cute. And that little mousy mouse has these really interesting curved ears, right? And they're kind of big. Why do you think they're curved like this? Why do you think the ears of a mouse are concave? Good question, huh? I don't know what I'm doing. I know I have another slide here, so I don't know why it's not getting me there. Exit and go. Oh, maybe that was my last slide. That's interesting. I didn't think it was. I'll rewind because that was really stupid. Oh, shoot. What did I do with my Screencastify?